Much of this course, we've concerned ourselves with nanotechnology from the point of view of its applications, from the perspective of what it can enable. And why not? I mean, so many of us are passionate about this field because of what we can do with it. But I think there's another interesting perspective to bring to the field, which is there are so many beautiful things that we can create, such amazing materials, such amazing images. Some of the pictures that people are taking on the nanometer length scale using their transmission electron micrographs or their scanning tunneling microscopes are so beautiful and so fascinating. I think it's interesting to view nanotechnology almost through the lens of art or design or architecture. So we'll start with the building blocks themselves, and then we'll think about the buildings. We'll think about what different types of structures we can engineer, and then how we can build those into more complex buildings from these building blocks. Here's a couple of examples of some of the more interesting building blocks. Think of it as kind of an artist's portfolio of what they can do. We have on the top left a nanoparticle, something we spend lots of time on throughout this course. It can be kind of approximately a sphere, although you can often see hints at it having crystal facets. And since these are crystalline arrays, they do possess facets. Those facets end up being the basis for a lot of the shapes that you see elsewhere here. The pyramids, the cubes, the structures that have a hexagonal cross-section, things that look like die that you might roll, or tetrapods, or pointed objects, or even stars. These structures are ultimately having their origins traceable to the underlying crystallinity that is at their base. Now, another thing that we can do, so the first thing you can imagine doing once you have a nanoparticle available, is that you can build further on top of it. And so people call these core shell structures. We can start with a particle having a particular crystal lattice, and then we can grow on top of it some kind of shell, typically of another material. We use the term epitaxy to describe the growth of crystals on top of other crystals. And key to the word epitaxy is the idea that the crystalline periodicity, the spacing amongst the atoms in the first material, is perfectly mimicked in the second material that lies on top of it. We use the term heteroepitaxy to describe the growth of a shell of a second type of material on top of a first material. Now, these heteroepitaxial core shell nanoparticles have properties that go well beyond those that are embedded in the cores alone. We've talked already about how with the core size, we can change quantum confinement. We can change the band gap of the structure. But with the shell, for example, we can wrap a core within a shell where the shell is prone to attract excited electrons into it, but it's prone to repel the lower energy electrons. And so it decreases the degree of overlap, if you like, between excited and less excited states. As a result, the transitions that can occur within a core shell nanoparticle can be different. If those overlaps are weak between the two states, the initial and the final state, we'll have a weak transition. We may have very poor luminescence from these materials. On the other hand, if we engineer a shell that's great at just cramming the electron in all of its possible states tightly inside the core, we can achieve a much more strongly luminescent structure. And so this is an example of something that we can do by engineering just on one more length scale beyond just the core itself, but by building these shells. In fact, we can build a quantum gobstopper. We can build structures that embed many, many layers of shells growing out of them, where each one of those layers is used to manipulate the structure of the material within. Now, when we talk about epitaxy and we talk about growth of crystals on other crystals, there we really need to think about these facets, these planes of atoms that exist. In fact, when you look at a nanoparticle and you think it's spherical, it really isn't. It may have many, many planes shaved off to look almost spherical, but it still has some structure. It has regions where certain atoms of one type are exposed, certain atoms of another type are exposed. Let's take as an example a binary material, one that consists of tin and sulfur. Well, if you were to slice it along certain axes, you could see tin and sulfur atoms in equal ratios, 1-to-1 ratio. But there are other axes on which you could slice it, the way you might imagine cleaving a diamond face. There are other axes where you would see only tin atoms, or axes where you'd see only sulfur atoms. But this in turn allows us to engineer the propensity for these materials or for these facets to react. And so this gives us the ability to differentiate certain facets from others. And so if you look at a nanoparticle that has an exposed facet off at some angle, well, perhaps we can engineer that facet to be one where we can grow an arm off of it while protecting the other facets that don't have the same degree of reactivity. Perhaps we can use organic molecules, such as these ligands that we've spoken about, to help us to keep one of those facets well protected, and we can make those organic ligands really pop off of the facet that we want to grow our arm on. And so we can further engineer the structural nature of these materials. Well, what can we do when we can control these facets? This is what really leads to the capacity to build things that are directional. And so you could say that our quantum dots, or we can call them three-dimensionally confined systems, where we've confined electrons in both horizontal planes and also in the vertical plane. We can call these three-dimensionally confined, or zero-dimensional from the point of view of the number of dimensions on which the states, the electronic states, are extended. Well, we can use that same concept to talk of materials that extend the electron along one axis but confine it along two. These we call one-dimensional materials, where there's a propagation direction, one propagation direction. We also have what are called quantum wells, where the electron can swim around freely within the plane and is confined along only one axis. Well, these are now the kinds of materials that we can grow with the power of controlling directionality through controlling the propensity to grow along certain facets. In fact, these ideas of 0D, 1D, 2D materials, these are really the same forces that are at work when we think about some of the carbon-based nanomaterials that are also so beautiful. Buckyballs have a lot in common with quantum dots in the sense that they're confined along all three axes. Nanotubes, rolled up sheets of graphene, allow propagation along their axis and confinement in the other two dimensions. If you unroll one of those carbon nanotubes, you produce a graphene sheet. Electrons can skirt around within the plane, can move freely, but they are confined to reside within that plane. So they function more like quantum wells. And so these semiconductors, these traditional inorganic semiconductor materials like silicon and germanium, with which we are able to grow various types of nanoparticles, and the carbon-based or organic materials such as the buckyballs, nanotubes, and graphene, they all have analogs of one another. They all can see different degrees of confinement and propagation engineered at the nanoscale. So that's one very useful length scale to operate at. It's the building block length scale. It's the particle length scale. But I think it's really interesting to think about whether we can build structures out of those particles. And the easiest kind of material to think about building would be another periodic structure. It would be another crystal. In fact, you could think of it as a supercrystal, a periodic array of nanoparticles, where, of course, each nanoparticle is itself internally a crystal. And here Chris Murray, who was at IBM in some of his earlier work and is now at the University of Pennsylvania, has done some incredible work where he's shown how to take the semiconductor nanoparticles and get them to pack into perfectly regular arrays. So you might wonder, what are the requirements for doing that? Well, there are a couple. The first is, to make a perfectly ordered structure, all of your building blocks have to be the same as one another. It's like building a salt crystal. It's because all the sodiums are the same as one another and all the chlorines are the same as the other chlorines that you can get a perfectly regular array. If you were to have a bunch of impurities in there, materials of different sizes included, you would eventually have a pretty big mess. And so building one of these supercrystals or superlattice materials is reliant on making all the nanoparticles the same. We call that property monodispersity. We call it the property of having every particle identical to all the others. And we've gotten pretty good at carrying out the synthesis of these nanoparticles to make them all identical. But when it's not perfect, even if it's not completely perfect, we have some other options available to us. For example, we're able to ensure that overly big nanoparticles that we don't want in the mix, we're able to cause them to precipitate out of solution. They can be particularly easy to cause to drop down to the bottom of the solution, so all we have left are the smaller particles of the right size. This process, known as size selective precipitation, has been used now for 2 decades in order to produce increasingly monodispersed, increasingly pure sets of nanoparticles. Now, the other ingredient that we need in order to build one of these supercrystals, something that's very regular, is we need some kind of strategy to allow every atom, every constituent nanoparticle to find its place in the lattice. And that typically involves kind of a slow annealing or a slow growth. It would be like trying to build a really nice, big, large, very organized crystal by allowing, say, the liquid in which the precursors were contained, think of salt once again, allowing that solution, say, allowing the water to evaporate very slowly, to give every atom lots of time to find just the right crucible where it could reside in the ordered structure. Well, in this case of building nanoparticle superlattices, exactly the same idea is used, and there's a very clever way to accelerate that, which is through solvent mixtures. So researchers don't just use one solvent containing all these nanoparticles dispersed in them, drop a drop, let it dry, but instead they use a pair of solvents. The majority solvent, the one which they use a preponderance of, is one that evaporates pretty rapidly, and then a small fraction, maybe 10%, will be one that evaporates much more slowly. And so they put a droplet of this onto typically a very smooth substrate, allow the rapidly evaporating one to evaporate, and then you're left with this kind of gooey mass where the nanoparticles are now in a very dense, concentrated solvent, and that solvent is evaporating very slowly. And as a result, every nanoparticle has a chance to kind of look around, feel its way around the growing crystal that's emerging, find its lowest energy site, so find the region which enables it to form an ordered structure. Now there's another particularly beautiful result that Chris Murray has achieved, which is not just to make these superlattices out of a single particle, but to make them out of multiple different types of particles. Now this reminds me a little bit of the amazing tiles that you can see often in the Middle East. If you go see some of the beautiful architecture there, you can see now periodic patterns that aren't just simple repetitions of a single repeat unit, but instead periodic patterns that have embedded within them sub-patterns as well. And so these kinds of mosaic or tiling ideas have led to what's become known as binary superlattices. In binary superlattices, they add in another ingredient. They add in another degree of freedom. They allow us to make materials that don't just have the properties of a first or a second constituent, but that fuse those properties. And so Chris Murray and his group have used these ideas to make sort of super semiconductor materials, ones based on two different types of constituents all ordered, and where the ability to propagate electrons and the ability to have an abundance of electrons are separately controlled through the two constituents that make up these materials. Some beautiful work also coming from Murray in collaboration with Dmitry Talapin, who was with him at IBM and who now runs his own research group doing very exciting work at the University of Chicago, has been to take these ideas of oriented attachment and to extend them not just from making these three-dimensional crystals, but taking individual nanoparticles and causing them to form a string, causing them to attach along a one-dimensional axis. As a result, they've made incredibly long wires, micrometers long, out of nanometer-sized materials. These are obviously very prone to carry electronic charge along their length while still having the confinement, the quantum confinement, along the direction that's perpendicular to the length axis of the wire. And the concept that they utilized, that they enabled them to explain how this worked was quite fascinating. It did involve these facets. It involved the fact that the constituent materials that are making up these crystals, they obviously like each other. The reason you make tin sulfide, the reason it's so naturally easy to make is that tin and sulfur really like each other. And so they made these nanoparticles consisting of tin and sulfur in equal concentrations, but where some of the exposed facets were tin-based and the others were almost purely sulfur-based. And so two nanoparticles would see each other, and if they ran into each other in solution and the sulfur facet was facing the tin facet, they would bind, and otherwise they wouldn't. And so they created an avenue towards then kind of a propagating idea where one got this growth of a longer and longer chain, and incredibly long, very ordered chains, and epitaxially connected chains, kind of using an idea of complementarity, almost a yin and a yang between the different facets of the nanoparticles being attracted to one another to form these oriented attachment structures. There are some other really interesting and actually quite powerful materials concepts that have been developed as well. One of them is the idea of engineering tetrapods. So these structures have a bunch of legs pointing downwards and then one kind of arm, or if you like, a body pointing upwards. And along that component that points upwards, of course, electron propagation is achieved very well. Well, this is actually a very useful architecture. The problem with wires on their own, or just nanorods, is that if you plonk them all onto a surface, if you just sort of coat them down, well, they'll naturally be prone to lie down on that surface. Very few of them would point up. In fact, often none of them can. But with these tetrapods, because of their legs, you can ensure that they all plant 3 of their legs on the surface, and they point their 4th extension upwards. And so now they have conduction in the vertical direction, and they have this orientation that's enforced by their underlying structure. In fact, you might wonder, how does it happen? How is that possible? Well, here we use crystals that form tetrahedral structures, so where they have 4 exposed facets, all equally prone towards growth, and then we grow off of those facets. So we kind of create 4 substrates at various angles to each other, off of which growth of the rods can occur. And we do it heteroepitaxially, typically. We do it with one material to form the body off of which growth can occur, and a second material that forms the basis for the arms. And so with this, researchers have achieved really incredible control over the formation of these new materials, which have all sorts of applications in making more controlled electronic structures. Now, this is a picture of something that looks like a pencil, and it gets called a nanopencil. In fact, you can even see the eraser on one side and a pointy end on the other. And what it illustrates, this is an example of a structure that hasn't yet found its utility. The eraser isn't actually used as an eraser. But what it illustrates is the idea that we are able now to combine multiple materials into a single nanoparticle. So we're able to include a metal here and a semiconductor over here. We're able to create a sense of orientation as well. And so this ends up being a very powerful idea. There's a front and a back to a structure, and so this is what allows things to form chains as a result of having a directionality to them. Another way to think of that is a polarization to it. There's a particular proneness for charge to flow in one direction. One can even imagine making little semiconductor materials, little junctions, little PN junctions or diodes, but now at the nanoscale and synthesized in solution. This is one of my favorite pictures. It's from some beautiful work that Jin Mu-cheon in Korea has done. It's one of his nano stars, and he's been one of the leaders in figuring out how to build such a diversity of different shapes. And he's really able to rationally engineer from a knowledge of the crystal structure that will exist, from a knowledge of the facets that will be exposed, how he can then grow these larger shapes which extend outwards in all sorts of interesting directions. I'd like to turn now, having spent some time on the building blocks, I'd like to turn to some of the architectures that we're able to create. And here I'd like to bring in DNA. DNA is a very powerful type of Velcro, effectively. We know lots already from this course about the specific binding properties of DNA. We know that a single strand of DNA, when it encounters a complementary sequence of DNA having exactly the complementary sequence, that they will bind, they will form the duplex, and that if there's a lack of a match, that they will not form that duplex. And so we have kind of a lock and key recognition system. It's like Velcro, but Velcro that will only stick to a very, very specific complementary piece of Velcro. Well, I think of this as just an incredibly powerful technique for the controllable construction of structures that combine a bunch of different nanomaterials. It allows us, when we kind of label various different nanomaterials with different sequences of our DNA Velcro, it allows us to engineer potentially a diversity of structures this way. So let me start with a simple structure, and I'll go to some more complex ones that have emerged very recently. So the simple structure is illustrated here. It involves a series of nanowires that are grown from the bottom up, and then it involves attaching a strand of DNA to the nanowires, a single-stranded piece of DNA, and that single-stranded piece of DNA has a functional group on the end of it that makes it really want to stick to the surface of these nanowires. We do the same thing in a separate reaction vessel with a bunch of nanoparticles, and there, though, we use a sequence of DNA that, of course, will bind at its end to the nanoparticles, and where that sequence is complementary to the one that we stuck on the rods. Then when we combine these two things, when we take the nanoparticles in solution and put them on top of these nanorods, there's an opportunity for specific hybridization to occur. So this image is showing, and this is actually some of Shana Kelly's beautiful work from a couple of years ago. This image is showing how we're able to sort of take two different classes of nanostructures and fuse them or combine them in a rational way in order to form a new nanostructured material. You can think of it as forming a nanostructured material building on a higher length scale or a higher degree, a higher order, a higher hierarchy as a result of combining pre-synthesized nanoparticles in a way that provides a lot of control. Well, this concept, the idea of hybridizing DNA with itself and then using as building blocks nanoparticles that have single strands tethered to one another, this is a concept that Shana and I thought was very interesting and that could allow us to engineer even more complicated structures than what we showed there. So our concept was this, that we could have a number of different nanoparticle types, perhaps different colors. We could have a red emitter that would emit light around 600 nanometer wavelength, a green emitter that would emit it around 500 nanometer wavelength, and a blue emitter in the sort of 400 nanometer wavelength range. And that we could label each one of these with a different sequence, a very carefully chosen sequence of DNA. And that furthermore, we thought that we could introduce the possibility of controlling how many DNA strands would adhere to each one of these nanoparticles, each one of these quantum dots. And you can see now already that we're starting to develop a bit of an analogy with the periodic table. In the periodic table that we spoke about earlier, we had this potential for 1 or 2 or 3 or 4 valence electrons to be available for binding. And the kind of marriages that are formed, the kinds of proclivities amongst different atoms in the periodic table, these are all determined by the valency, by the number of electrons available for binding on the outer surface. Well, with this DNA concept, we were kind of building an analogy with that valency idea. We were putting a programmable number of different strands on the surface. And so when we started with a large inner nanoparticle having let's say 4 pieces of DNA on it that displayed a certain sequence, when we then introduced to couple to that, say a green class of nanoparticles having the complementary sequence, we were able to ensure that the center nanoparticle had exactly 4 green nanoparticles bound to it. And then we were able to extend this idea even further. We were able to introduce a third class of nanoparticles that would bind to the second class of nanoparticles. So we were able to build from an inner core nanoparticle, we were able to build crosses or triangular structures, and then we were able to build out from there as well. Well, once we've made these things, initially we did it because it seemed like such a fascinating challenge that you could build designer nanostructured materials, kind of an analogy with building molecules from the atoms in the periodic table, that you could design these nanostructured materials in a controlled fashion, and all you had to do was kind of combine ingredients. You didn't have to do anything yourself at the nanoscale. You just got all of these materials to organize. So it seemed like just a neat thing to do and something that led to some beautiful images, some very aesthetically appealing results. But nevertheless, once we built these structures, we asked ourselves, well, what kind of special properties do they have? How do they behave like things that go beyond just kind of mixing together 2 vats or 3 vats of materials? How do they actually evince the fact that we've coupled these materials to one another? And where we went looking was on how energy is communicated amongst these nanoparticles. So we actually ended up making a structure where the outermost set of nanoparticles possessed excited electrons when you illuminated it at the highest available energy state, and that the inner ring had a sort of middling energy excited state level, and that the very heart of the structure had the lowest energy. And what that meant is that when we photoexcited the outer ring, energy was very inclined to trickle downhill. And so the energy would pour into the inner shell, and then the energy would further pour all the way into the very center constituent nanoparticle. And the way we were able to see this, the way we were able to measure this was that even though we were exciting very brightly luminescent materials in the outer ring, once we coupled them into these called artificial molecules, as we termed them, We were no longer able to see any light coming out of the materials on the outer shell because they transferred it all into the heart of our structure. So we'd really built an energy funnel. We kind of built a concentrator where we could illuminate one of these complexes, or in fact we were illuminating many of these complexes at the same time. And we could have an absorption from this complex that was proportional to the number of nanoparticles. These complexes are starting to get quite big, so they had quite large absorption. But all of the energy would be funneled within the complex because of the architectures that we've built. It would all be funneled towards the center material. And we realized once we'd done this, and once we saw the results, which were so striking, I mean, the spectra just spoke eloquently to us that we'd really coupled strongly together these nanoparticle structures. We realized that we had really built something that was an analogy with the way in which the photosynthetic apparatus acts in plants. In plants, there exist what are called light harvesting antennas. And in these, the idea is that if only the regions that actually translated photonic energy into excited states, translated that into stored chemical potential energy, if only those reaction centers were present, then the efficiency of plants, of leaves, would be very, very low because the absorbance from those centers would be very low. So instead, plants have evolved systems that function like antennas. They actually kind of extend their reach for light absorption the way an antenna extends its reach for the absorption of electromagnetic radiation of radio waves. They extend this reach, and then they all funnel all of that energy down towards the reaction center. Well, we had done the same thing with these multi-length scale structured molecular complexes, and we had showed that the efficiency with which we're able to capture and transfer the energy towards our virtual reaction center was extremely high. Almost all of the energy ended up right at the heart of these structures. The other concept that I found very appealing about this work was just that it turned out to be a tunable reaction. This is something that one doesn't find in the photosynthetic apparatus, but we were able to turn on and off this phenomenon. And the way we did that is we just changed the pH within these structures, or within the solutions these structures found themselves in. And so at certain pHs, the charge on these materials was revealed. It was exposed effectively. And because all of the different constituents of these artificial molecules had the same charge, they were prone to repel each other. Now, we detached them too tightly for them to blow up. But what happened is they took an extended conformation. They spread out. And so the constituent particles are now far apart, and the amount of energy transfer was essentially turned off. And so when these were in their extended state that we controlled through the solution conditions, every nanoparticle acted essentially like an independent nanoparticle. There was no energetic coupling. But when we changed the pH in order to enable these structures to collapse or condense into smaller, more dense structures, only then did we turn back on this reaction. And so we'd made a tunable system. I mean, it was always functioning as a light harvester, but we were able to turn on and off its funnel. We were able to turn on and off its propensity to transfer the energy to the reaction center. Another way to think about it is we made a pretty good sensor for pH. We were able to test the acidity or the basicity of the solution that our nanoparticles were in through the spectral signatures that were coming out of the light that was being emitted from these materials. And my final example for this lecture on nanomotifs draws in the work of Angela Belcher, a professor who does incredible stuff at MIT. Professor Belcher has really made her name by merging the world of the biological, including things like viruses, with the world of nanoparticles. And what she's been able to do is build viruses that have coats that are particularly prone to grow certain nanoparticles on their surfaces. And so she's able to engineer materials which take on the shape of the virus because she's able to effectively epitaxially grow semiconductor nanoparticles off of the surfaces of these viruses in a very selective way. And she's further combined that field of semiconductors and material science with the field of genetic engineering in that she's been able to find which proteins displayed on the surface of these viruses allows her to grow with particular success, with particularly high yield, these nanostructured materials. And so it illustrates the fact that when we think about building nanomotifs, we don't have to limit ourselves to thinking only about, say, inorganic semiconductors or only about organic materials like buckyballs and nanotubes, but that we can even get biological entities and even life forms in this case into the game for engineering on many length scales. To summarize this lecture, we've seen that nanotechnology clearly provides us with this incredible diversity of building blocks. It goes well beyond the quantum dots that we've seen lots of, or rods, but it also, through the crystal facet engineering capability, it allows us to build structures that are beautiful and fascinating. They remind me a little bit of the shape games that my two-year-old plays at home, where he's able to match his triangle up with a triangle in his puzzle, and it's such a diversity of interesting shapes that are beautiful and fascinating to look at. I think we've just scratched the surface of what we can do on that front, but we certainly already can do a lot of things. Once we have these building blocks, the next step in nanotechnology is that we take them, we typically have to functionalize them, we typically have to do something so that they're prone to interact with each other in a certain way. And when we do this, we're able to make structures that are like tiled mosaics in the case of superlattices, or that form extended crystals along a single axis like the oriented attachment wires. And then finally, especially when we bring in biology, when we bring in the power of DNA specificity, or when we bring in the capability to build a nanostructure on the code of a virus, we can go higher and higher in the hierarchy of building up these structures. It's really the idea of specificity that enables this remarkable degree of control, all of it engineered from the bottom up.